In the darkness 6 billion kilometers from the sun, a world is redefining our understanding of the solar system. Once considered the solar system's lonely ninth planet, it now reveals astonishing vitality of an icy world. This is Pluto, a place far more magical than imagined. Welcome to the Cosmic Guide to Sleep. Today we will together unveil Pluto's mysteries, following New Horizons probe's trail, venturing deep into this distant frozen kingdom. The final decade of the 19th century, astronomy underwent profound transformation. New telescope technologies constantly advanced. Photography began applying to astronomical observations. But what most puzzled astronomers was Uranus's orbital anomalies. After William Herschel discovered Uranus in 1781, astronomers began recording its trajectory. However, observational data showed Uranus's actual position always had slight deviations from theoretical calculations. Though this deviation was only a few arcseconds, it was enough to unsettle the entire astronomy community. French mathematician Urbain Le Verrier, a scientist renowned for precise calculations, successfully predicted Neptune's existence in 1846. Through complex orbital mechanics calculations, he accurately forecasted Neptune's position. This achievement shook the entire scientific community. Le Verrier's accomplishment inspired more astronomers. They began suspecting, beyond Neptune's orbit, other unknown planets might exist, because even considering Neptune's gravitational influence, Uranus's orbit still showed unexplained deviations. Against this scientific backdrop, American astronomer Percival Lowell entered the historical stage. Lowell came from a prominent Boston family, having sufficient wealth to support his research. He was famous for studying Martian canals, but his greater dream was finding unknown solar system members. In 1905, Lowell began systematic searches for an unknown celestial body he called Planet X. In Flagstaff, Arizona, he established Lowell Observatory at 2,210 meters altitude, with excellent atmospheric stability, an ideal location for astronomical observation. Lowell Observatory was equipped with the most advanced telescopes of that era, including a 61-centimeter reflecting telescope and a 33-centimeter refracting telescope. These instruments were top-tier for their time. Lowell developed unique search methods. He would photograph the same sky area on different nights, then use a blink comparator to compare star points in two photos, looking for celestial bodies that had moved position. This method seemed simple, but was exceptionally difficult in practice, because it required comparing thousands of star points, and planetary movement was very slow, needing photos taken days apart to detect. From 1905 to 1915, Lowell conducted systematic searches. He focused on areas near the ecliptic, where planets were most likely to appear. During this time, he discovered many new nebulae and galaxies, but never found Planet X. In 1915, Lowell published his research results. Based on orbital deviations of Uranus and Neptune, he calculated Planet X's mass, about 7 times Earth's mass, approximately 43 astronomical units from the Sun. These calculations later proved erroneous, but were the most advanced research at the time. On November 12, 1916, Lowell died from a stroke. His search work was forced to halt. More regrettably, on March 19 and April 7, 1915, his observatory had actually photographed Pluto, but due to poor image quality, and Pluto being much fainter than expected, this discovery was missed. After Lowell's death, his widow Constance Lowell became involved in prolonged legal disputes with the observatory. This caused search work to stall for 10 years. Until 1927, the observatory regained sufficient funding to continue searching for Planet X. In 1929, a young amateur astronomer, Clyde Tombaugh, caught Lowell Observatory's attention. Tombaugh was born on a Kansas farm, filled with passion for astronomy since childhood. Using discarded farm machinery parts and lenses, he built his own telescope. His drawings of Mars and Jupiter observations revealed remarkable talent and patience. Observatory director Vesto Slifer invited Tombaugh to join the search team, entrusting him with continuing the Planet X mission. Tombaugh improved observation methods, using more sensitive photographic plates with longer exposure times. This could capture fainter celestial objects. Tombaugh's work was exceptionally tedious. He needed to photograph the night sky daily, then during daytime use the blink comparator. Carefully compare photos taken days apart. This process required immense patience and concentration. Any minor oversight could miss important discoveries. On January 23 and 29, 1930, Tombaugh photographed the Gemini region. These images would change astronomy history. On February 18 at 4 p.m., while comparing these two photos, he noticed a 15th magnitude star point had moved within the star field. Tombaugh immediately realized this might be the Planet X they had sought for years. He rushed excitedly into Slifer's office, reporting this major discovery. Subsequent observations confirmed this object's movement. It was indeed a new planet. On March 13, 1930, Lowell Observatory officially announced discovery of the solar system's 9th planet. This day coincided with Lowell's 75th birthday and the 149th anniversary of William Herschel's Uranus discovery. After the news broke, the global astronomy community was electrified. But this discovery also sparked some controversy, because later research showed Pluto's mass was too small to possibly cause Uranus's orbital perturbations. The original orbital deviations were actually observational errors. Pluto's discovery process was filled with chance and necessity. It was both a product of mathematical prediction and result of meticulous observation. Moreover, the culmination of generations of astronomers' persistent efforts. Looking back at this history, we can't help but reflect. Scientific discovery often follows this pattern. Necessity mixed with chance. Chance containing necessity. Pluto's story exactly embodies the spirit of scientific exploration. From Lowell's theoretical predictions to Tombaugh's patient searching, from mathematical calculations to practical observation, every link was indispensable. This is the true essence of scientific research. Theory guiding practice, practice verifying theory. Pluto's discovery not only expanded human knowledge of the solar system, but also demonstrated the unique charm of scientific exploration. Tells us, even the smallest clues, the most improbable guesses, deserve pursuit with the most rigorous attitude. Today, looking back at this history, we can still feel the passion and dedication of those early astronomers. Their stories will forever inspire successors to continue exploring cosmic mysteries. When Pluto was discovered in 1930, astronomers quickly realized this new world differed fundamentally from other solar system planets. Its orbital characteristics were so peculiar that for decades afterwards, it consistently challenged traditional understandings of planets. Pluto's orbit forms an extremely elongated ellipse, with an eccentricity of 0.248, the highest among known planets at that time. In comparison, Earth's orbital eccentricity is merely 0.0167. Neptune's only 0.0086. This special orbit brings Pluto within 4.4 billion kilometers of the Sun at perihelion, equivalent to 29.7 astronomical units. Surprisingly, this position actually places Pluto closer to the Sun than Neptune's orbit. For 20 years between 1979 and 1999, Pluto was indeed nearer to the Sun than Neptune. The orbit's aphelion extends even farther, reaching 7.38 billion kilometers, approximately 49.3 astronomical units. This means Pluto's distance from the Sun varies by nearly 3 billion kilometers. Such extreme distance variation causes received solar radiation energy to change threefold during its orbital period. Pluto's orbital period spans 248.09 Earth years. This number itself is interesting because it forms a 3:2 orbital resonance with Neptune's 164.8-year orbit, meaning when Neptune completes 3 solar orbits, Pluto completes exactly 2. This precise orbital resonance ensures these two bodies never collide, although their orbits cross paths in space. More surprising are Pluto's rotation characteristics. Its axial tilt reaches an astonishing 122.5 degrees, meaning Pluto essentially orbits on its side. By comparison, Earth's axial tilt is only 23.5 degrees. Uranus's 98 degrees was already considered large, but Pluto's tilt is even more extreme. This extreme axial tilt causes exceptionally dramatic seasonal changes on Pluto during its 248-year orbital period. Different latitudes experience extraordinarily long polar days and nights. During certain periods, an entire hemisphere remains sunlit for decades, while the other hemisphere plunges into equally prolonged darkness. Pluto's rotation period is 6.387 Earth days, relatively slow in pace, but interestingly, its largest moon Charon shares exactly the same rotation period, because both bodies are mutually tidally locked, forever showing the same face to each other. Regarding Pluto's physical characteristics, its diameter measures approximately 2,376 kilometers, equivalent to 18.7% of Earth's diameter, 1/3 smaller than our Moon. Accurate determination of this size took a lengthy process. Early estimates contained significant errors. Not until New Horizons' 2015 flyby were precise measurements obtained. Pluto's mass is 1.303 times 10 to the power of 22 kilograms, merely 0.218% of Earth's mass. Through precise observations of the Pluto-Charon system's orbit, scientists calculated their combined mass, then estimated Pluto's density from volume, approximately 1.854 grams per cubic centimeter. This density suggests Pluto likely constitutes a differentiated body, with a rocky core and icy mantle. Pluto's surface temperature is extremely low, averaging -229 degrees Celsius. In such frigid conditions, many substances exhibit peculiar properties. Nitrogen, methane, and carbon monoxide, gases that are normally gaseous on Earth, all exist in solid form on Pluto's surface. Pluto possesses a thin but complex atmosphere, primarily composed of nitrogen, accounting for 98%, also containing methane and carbon monoxide. Atmospheric pressure is extremely low. Surface pressure measures only 1/1,000,000th of Earth's. This atmosphere undergoes significant expansion and contraction as Pluto's distance from the Sun changes. When Pluto approaches perihelion, surface ices sublimate. The atmosphere becomes relatively thick. As it moves farther from the Sun, most gases recondense, falling to the surface as frost. This breathing-like cycle keeps Pluto's atmosphere in continuous transformation. Pluto's surface albedo varies considerably, ranging from 0.1 to 0.7, meaning some regions appear very dark, while others are exceptionally bright. These significant albedo differences hint at complex surface composition and geological history. Through spectroscopic observations, scientists detected presence of nitrogen ice, water ice, methane ice, and carbon monoxide ice on Pluto's surface. These volatile ices distribute unevenly under Pluto's changing surface temperatures. They undergo phase transitions and flow, creating unique geological features. Pluto's surface gravity is very weak, only 6.2% of Earth's, meaning a person weighing 70 kilograms would weigh merely 4.3 kilograms on Pluto. Such minimal gravity makes it difficult for Pluto to retain substantial gases. This partially explains its thin atmosphere. Pluto's escape velocity is only 1.2 kilometers per second. By comparison, Earth's escape velocity is 11.2 kilometers per second. Such low escape velocity allows atmospheric molecules to easily escape into space. Without continuous gas replenishment, Pluto's atmosphere would quickly dissipate. Interestingly, despite Pluto's small size, it exhibits significant internal layering. Through analysis of its density and gravity field, scientists infer it likely possesses a rocky core about 1,700 kilometers in diameter, encased in a 300 to 400 kilometer thick icy mantle, topped by an outer crust of various volatile ices. This internal structure suggests Pluto may have experienced significant thermal differentiation during formation. Its internal temperature was once sufficiently high for heavy materials to sink, forming a core, while light materials rose, forming mantle and crust. More surprisingly, evidence indicates Pluto's interior might still retain some heat. This could explain why this distant small world displays such active geological features. Pluto's orbital characteristics create another interesting phenomenon, with orbital inclination reaching 17.16 degrees. Relative to the ecliptic plane, it actually orbits on a distinctly tilted plane, making its orbit notably different from those of other planets. All these unique orbital and physical characteristics make Pluto truly distinctive in the solar system. It resembles neither traditional terrestrial planets nor gas giants or ice giants, instead representing an entirely new celestial category. This uniqueness ultimately prompted astronomers to reconsider how to define the fundamental concept of a planet. When we deeply understand these Pluto characteristics, we comprehend why its identity sparked such controversy, and better appreciate this distant world's unique position in the solar system. It not only expanded our understanding of planetary diversity, but also opened a new chapter in Kuiper Belt object research. The controversy surrounding Pluto's planetary status did not begin with the famous 2006 International Astronomical Union vote, but was foreshadowed from the moment of its discovery. This decades-long scientific debate reflects humanity's continuously deepening understanding of the cosmos and demonstrates the scientific community's courage in self-correction. When Pluto was first discovered in 1930, its mass was severely overestimated. Initially, scientists at Lowell Observatory estimated its mass comparable to Earth's. This erroneous estimation largely stemmed from limitations in observational data and theoretical expectations about Planet X at that time. As observational technology advanced, astronomers began noticing anomalies. Pluto's brightness was unusually faint. Even at its maximum brightness, It only reached magnitude 14. This suggested its size might be much smaller than expected. In 1950, American astronomer Gerard Kuiper, using the then state-of-the-art 5-meter Hale telescope, conducted the first precise measurements of Pluto, determining a diameter of only 5,800 kilometers. Though this value remained too large, it was considerably smaller than initial estimates. The real turning point came in 1978, when James Christie at the U.S. Naval Observatory, while examining photographs of Pluto, noticed periodic bulges in the stellar image. This discovery led to finding Pluto's first moon, Charon. Charon's discovery enabled scientists to apply Kepler's third law and accurately calculate Pluto's mass. The results were shocking. Pluto's mass was merely 0.2% of Earth's. This figure was less than 1/10 the Moon's mass. Such a small mass could not possibly cause orbital perturbations in Uranus and Neptune. This meant Pluto's discovery was actually a beautiful accident. In the early 1990s, with the Hubble Space Telescope's deployment, astronomers obtained clearer images of Pluto. These images revealed Pluto's diameter was only about 2,300 kilometers, smaller than many scientists had expected. This further undermined its planetary status. Meanwhile, the Kuiper belt beyond Pluto's orbit began revealing its true nature. In 1992, astronomers David Jewitt and Jane Liu discovered the first Kuiper belt object, 1992 QB1. This discovery confirmed Kuiper's 1951 theory that beyond Neptune's orbit exists a disk-like region composed of icy bodies. Subsequent discoveries followed rapidly. Thousands of Kuiper belt objects were found, many with orbital characteristics surprisingly similar to Pluto's. This prompted astronomers to consider whether Pluto was just an ordinary member of the Kuiper belt. The controversy ignited in 2005, when Mike Brown's team at Caltech announced discovering a Kuiper belt object larger than Pluto, initially designated 2003 UB313, later named Eris. Measurement data showed Eris's diameter was approximately 2,326 kilometers, slightly larger than Pluto. It also possessed moons, had greater orbital eccentricity, and averaged 3 times Pluto's distance from the Sun. This discovery forced astronomers to a crossroads. If Pluto was a planet, then larger Eris should also be a planet. And by this standard, the solar system might have dozens or even hundreds of planets. The International Astronomical Union recognized the need for a clear scientific definition of planet. Otherwise, the solar system's planetary list would extend indefinitely. In August 2006, the 26th General Assembly in Prague became the climax of this controversy. The Assembly established a Planet Definition Committee, comprising experts from astronomy, history, writing, and other fields. They proposed a 3-criterion planetary definition. First, the body must orbit the Sun. Second, have sufficient mass for hydrostatic equilibrium, assuming a nearly round shape. Third, must have cleared the neighborhood around its orbit. Pluto met the first 2 conditions, but failed the crucial third. Within Pluto's orbital region exist numerous other Kuiper belt objects. It has not cleared its orbital neighborhood. Heated debates continued for days. Astronomers worldwide expressed diverse views. Some scientists adhered to traditional planetary concepts, arguing Pluto should retain planetary status. Others advocated strict scientific definitions, believing emotion and history shouldn't influence scientific classification. The most dramatic moment came on voting day. The initially proposed resolution suggested expanding planets to 12, including Pluto, Charon, Ceres, and Eris. But this proposal faced opposition from most astronomers. The revised new resolution strictly limited planetary definition to bodies meeting all three criteria. By this standard, Pluto was reclassified as a dwarf planet, placed in the same category as Ceres Eris and other bodies. The final vote occurred on August 24, 2006, with over 2,500 astronomers from 75 countries participating. The voting results: 237 in favor, 157 against, with 17 abstentions. Pluto officially lost its planetary status. This decision immediately sparked strong reactions. Public response was particularly intense. Many expressed dissatisfaction with Pluto's demotion. In some U.S. states, resolutions were even passed, rejecting the IAU's decision. Divisions also existed within the scientific community. New Horizons principal investigator Alan Stern publicly criticized the decision, considering the definition seriously flawed. By these standards, planets like Earth, Jupiter, Neptune also cannot completely clear their orbital neighborhoods. Opponents pointed out the orbital clearance criterion contained ambiguities, especially during planetary formation stages. No planet could completely clear its orbit. Moreover, this standard meant the same celestial body in different stellar systems might receive different classifications. Supporters argued the new definition had clear physical basis, could clearly distinguish different celestial body types. The dwarf planet concept actually elevated these bodies' scientific status, making them independent research subjects. Culturally, Pluto's demotion had profound impacts. Textbooks required rewriting. Planetarium exhibits needed updates. Even astrology communities had to adjust their systems. However, scientifically, this reclassification brought positive effects. It prompted increased attention to Kuiper Belt object research, advanced outer solar system exploration. Pluto was no longer seen as an anomalous planet, but became an important window understanding the Kuiper Belt. More ironically, shortly after Pluto's demotion, New Horizons probe data revealed this icy world's geological complexity far exceeded all expectations. It possessed towering water ice mountains, vast nitrogen ice plains, possible subsurface oceans, even showing ongoing geological activity. These discoveries prompted new reflections. If planetary definition relied solely on orbital dynamics, while ignoring geological complexity, was such a definition sufficiently comprehensive? Some scientists began proposing including geological activity in planetary definition criteria. In 2018, during an academic conference in Texas, scientists revisited planetary definition issues, proposing new suggestions, defining planet as a substellar mass body that has never undergone nuclear fusion and has sufficient self-gravitation to assume a spheroidal shape, orbiting a star. By this definition, Pluto would regain planetary status. Solar system planets would expand to about 110. But this proposal hasn't been formally adopted by the IAU. The Pluto status controversy essentially reflects the nature of scientific development. Scientific knowledge isn't immutable truth, but continuously revises and improves based on new evidence and understanding. This controversy also teaches us classification itself is merely a human tool for understanding the world. What matters is the celestial body's scientific value. Regardless of designation, Pluto remains an extremely interesting research subject, continues providing us important clues about solar system formation and evolution. Today, as a representative dwarf planet, Pluto leads our exploration of Kuiper Belt mysteries. The story reminds us, science always welcomes new discoveries. Each update in understanding represents significant progress in human cosmic comprehension. On science's exploratory path, there are no eternal conclusions, only continuously deepening understanding. The Pluto controversy perfectly embodies this scientific spirit. On January 19, 2006, a special moment at Cape Canaveral, Florida, an Atlas V rocket carrying the New Horizons probe broke through Earth's atmosphere, headed straight for the solar system's edge. This 478-kilogram probe, bearing humanity's expectations and curiosity, began its epic journey. Its target was that never-before closely explored world, Pluto. New Horizons journey planning was extremely precise. It first utilized Jupiter's gravitational slingshot effect, flying through the Jupiter system in February 2007. This flyby not only accelerated the probe's speed, but also provided important testing opportunities for its scientific instruments. During the Jupiter flyby, New Horizons transmitted astonishing images, including detailed structures of Jupiter's atmosphere and volcanic eruptions on Jupiter's moon Io. These achievements filled the mission team with confidence for subsequent exploration. After 9 years and 6 months of long travel, crossing 4.8 billion kilometers of cosmic space, New Horizons finally on July 14, 2015, experienced its historic encounter with Pluto. Months before closest approach, New Horizons began transmitting surprising images. These images revealed Pluto wasn't the crater-covered dead world. As expected, as distance continuously decreased, more details gradually emerged. The most striking discovery was that huge heart-shaped feature spanning Pluto's surface. This, later named Tombaugh Regio, immediately became a global focus. On July 4, 2015, just 10 days before closest approach, New Horizons experienced a serious malfunction. Mission Control suddenly lost contact with the probe. After tense 90 minutes, engineers re-established communication, later discovered to be a computer reboot. Fortunately, automatic systems successfully restored normal operation. At 7:49 a.m. local time on July 14th, New Horizons flew past at 14 kilometers per second, from 12,500 kilometers above Pluto's surface. These were the mission's most critical 24 hours. All 7 scientific instruments activated, fully collecting every detail of this unfamiliar world. During the flyby, New Horizons' LORRI camera captured the clearest Pluto images to date, with resolution reaching 80 meters per pixel. These images revealed an extremely geologically active world. West of Tombaugh Regio, New Horizons discovered water ice mountains reaching 3,500 meters. These mountains' geological age might be under 100 million years. Quite young on cosmic timescales. Between mountains spread vast nitrogen ice plains. These ice plains showed almost no impact craters, indicating ongoing surface renewal. More surprisingly, in Sputnik Planitia, New Horizons observed features resembling cellular convection. Huge nitrogen ice blocks, slowly moving across the surface through thermal convection, creating unique polygonal patterns. Pluto's atmosphere also brought surprises. The probe observed complex atmospheric structures. Although atmospheric pressure was only 1/1,000,000th of Earth's, it contained multiple haze layers, extending 200 kilometers above the surface. When New Horizons passed through Pluto's shadow, it looked back at the sunlit atmosphere, capturing spectacular backlit images. These images revealed Pluto's atmosphere displayed beautiful blue coloring, caused by sunlight scattering through haze particles. On Pluto's surface, New Horizons also discovered various organic compounds, including complex molecules like tholins. These discoveries increased possibilities that Pluto might host prebiotic chemical processes. Observations of Pluto's satellite system also brought unexpected discoveries. Charon's surface showed complex terrain divided by cracks and canyons, most notably a 1,000-kilometer-long fracture zone, hinting this moon once possessed a subsurface ocean. Small moons Nix and Hydra displayed irregular shapes and unusual rotation. Their surface albedo varied greatly, showing complex geological history. New Horizons also first precisely measured Pluto's size. Diameter 2,377 kilometers. Slightly larger than previous estimates. This measurement confirmed Pluto as the largest known Kuiper Belt object. The probe's particle and plasma instruments recorded data on Pluto's solar-wind interaction, showing this distant world, despite thin atmosphere, still interacts complexly with solar wind. After flying through the Pluto system, New Horizons continued deeper into the Kuiper Belt. Its next target, 2014 MU-69, later named Arrokoth. On January 1, 2019, New Horizons successfully flew past this snowman-shaped object. Transmitted images revealed it comprised two lobed sections, surface displaying particular redness. This discovery provided important clues for studying solar systems' early formation. New Horizons mission data transmission lasted full 16 months, not completed until October 2016. This data totaled over 50 gigabytes, containing thousands of images and millions of measurements. These discoveries completely changed scientists' understanding of Kuiper Belt objects. Pluto was no longer the simple ice ball imagined, but a complex, dynamic world with active geological processes and surprising diversity. The mission team continues analyzing New Horizons observational data. Each new analysis potentially brings breakthrough discoveries. The probe remains operational, continuing further into distant cosmic space. New Horizons' success demonstrated the greatness of human exploration spirit. It showed us, even the most distant worlds deserve our exploration and understanding. Each new discovery expands humanity's cognitive boundaries. This brave probe not only brought back Pluto's secrets, but also inspired our courage to continue exploring the universe. Its story will forever inspire successors to continuously advance into unknown territories. New Horizons probes transmitted data completely subversion scientists' understanding of Pluto. This distant icy world displays astonishing geological activity and complex atmospheric phenomena. Its activity level far exceeds anyone's expectations. Pluto's geological activity first manifests in its young surface features. In the vast Sputnik planitia, New Horizons observed areas almost completely lacking impact craters. This discovery is astonishing because similar regions on other solar system bodies are typically covered with ancient impact craters. By counting crater densities, scientists calculated this plane's geological age might be under 100 million years. In the solar system's 4.56 billion year history, this equates to recent formation. More surprisingly, this nitrogen ice plain shows clear convection characteristics. Huge nitrogen ice blocks slowly move through thermal convection, forming unique cellular structures, each cell measuring 16 to 40 kilometers in diameter. These convection cells' existence indicates Pluto's interior still maintains considerable heat. Pluto's surface water ice mountains also display youthful characteristics. In Hilary Montes and Norgay Montes, scientists observed steep cliffs and sharp ridges. These topographic features typically mean they haven't experienced sufficient time for weathering erosion processes. Particularly noteworthy, some mountain slopes show flow features resembling Earth's glaciers. These structures, named glaciers, comprise nitrogen ice and other volatile ices. At Pluto's extremely low temperatures, they can still flow slowly. Perhaps the most surprising discovery: possible cryovolcanoes on Pluto's surface. In Right Mons region, New Horizons photographed a huge feature about 150 kilometers in diameter, with a central depression, surrounded by raised ridges. This terrain strongly resembles cryovolcanic features on other solar system bodies. Spectral analysis of Right Mons shows this region rich in water ice and ammonia hydrates. These substances' discovery further supports the cryovolcano hypothesis. If confirmed, Pluto would become the first Kuiper Belt object with discovered cryovolcanic activity. Pluto's geological activity might originate from internal heat sources. Scientists believe its internal heat mainly comes from radioactive element decay in rocks and primordial heat accumulated during formation. More profoundly, Pluto might possess a liquid subsurface ocean located dozens of kilometers beneath the ice crust. This ocean might contain substantial ammonia, acting as natural antifreeze, keeping water liquid. At extremely low temperatures, Pluto's atmosphere also displays astonishing complexity. Although its surface pressure is only 1/1,000,000th of Earth's, this thin atmosphere has fine structures and dynamic changes. The main atmospheric component is nitrogen, comprising 98% of total volume, also containing methane and carbon monoxide. These gases' proportions change significantly as Pluto moves along its orbit. When Pluto approaches perihelion, solar radiation makes surface nitrogen ice sublimate. The atmosphere becomes relatively thick. Near aphelion, most gases recondense, falling to the surface as frost. This seasonal variation makes Pluto's atmosphere experience periodic expansion and contraction. During its Pluto flyby, New Horizons observed multiple haze layers. These haze layers extend 200 kilometers above the surface, much higher than scientists expected. Analysis of haze particles indicates they form through photochemical reactions of nitrogen and methane under solar ultraviolet radiation. These tiny particles slowly settle under gravity, forming red organic deposits. On Pluto's surface, Pluto's atmosphere also shows clear thermal structure. Starting from the surface, temperature decreases with altitude, reaching minimum at 30 kilometers height. Then, in an inversion layer, temperature begins rising again. This thermal structure characteristic interesting similarities with Earth's troposphere and stratosphere. Although their composition and density differ greatly, Pluto's atmospheric circulation system also displays unique features. Due to slow rotation speed, weak Coriolis effect, atmospheric circulation patterns remain relatively simple, mainly showing global circulation from dayside to nightside. However, topography's influence on atmospheric motion is quite significant. Above mountains and basins, cloud-like structures observed. These might form through topographic lifting, causing gas condensation. Particularly interesting, Pluto's atmospheric escape rate is much higher than expected. Due to weak gravity, atmospheric molecules easily reach escape velocity. Estimates suggest Hundreds of tons of gas escape from Pluto's atmosphere into space every second. This continuous atmospheric escape might significantly impact Pluto's long-term evolution. It not only explains why Pluto's atmosphere is so thin, but might also closely relate to its surface feature evolution. Pluto's surface color variations also reflect its geological and atmospheric process complexity. From dark red Cthulhu Regio to bright Tombaugh Regio, these color differences originate from different surface compositions and degrees of space weathering in darker regions, likely rich in complex organic compounds, formed from methane under cosmic ray radiation. These substances, called tholins, also found on other solar system bodies. In brighter regions, mainly water ice and nitrogen ice, these ice layers reflect more sunlight, making these areas appear brighter. Pluto's geological and atmospheric processes don't occur in isolation. Complex interactions exist between them. For example, atmospheric seasonal changes drive volatile ice redistribution, while surface geological activity affects atmospheric composition and circulation. These discoveries indicate, although Pluto is so distant from the Sun, it remains a dynamically changing world. Its geological activity, intensity, and duration far exceed scientists' initial expectations. Studying Pluto's geology and atmosphere not only changed our understanding of this specific body, but also reshaped our comprehension of Kuiper belt objects. If dwarf planets like Pluto can maintain such active geological processes, then other Kuiper belt objects might be more active than we imagined. These understandings' importance extends beyond solar system science. They provide important references for understanding exoplanet system diversity. Pluto's example shows even small bodies far from stars might maintain long-term geological activity through internal heat sources, possibly even having environmental conditions suitable for life existence. As New Horizons data analysis continues, scientists believe more Pluto surprises await discovery. This distant world will continue challenging our understanding, pushing planetary science forward. Pluto itself is not the only enigma. Its satellite system is equally astonishing. This system, comprising Pluto and 5 moons, displays unique characteristics within our solar system. Its complexity far exceeds scientists' initial expectations. Let's begin with the largest moon, Charon. On June 22, 1978, James Christie at the U.S. Naval Observatory, while examining photographic plates of Pluto, noticed an unusual phenomenon. Pluto's image showed periodic bulges. This subtle observation ultimately led to Charon's confirmation. Charon's diameter measures approximately 1,212 kilometers, over half of Pluto's diameter. Such a massive ratio is unparalleled in our solar system. Indeed, the Pluto-Charon system's barycenter lies about 1,200 kilometers outside Pluto, making them more like a binary system than a traditional planet-moon system. These two bodies have achieved mutual tidal locking. They forever show the same face to each other. In Pluto's sky, Charon remains fixed in one position, never rising or setting. This synchronous orbital phenomenon results from billions of years of gravitational interaction. Charon's surface features are equally fascinating. Images returned by New Horizons reveal this moon possesses a dark red polar cap nicknamed Mordor. This region's red material is believed to be methane molecules from Pluto's atmosphere, transformed by radiation on Charon's surface. More surprisingly, Charon's surface shows a 1,600-kilometer-long canyon system and a massive dark area named Mordor Macula. These features suggest Charon might have possessed a subsurface ocean historically, possibly even experiencing geologically active periods. Now let's turn to the other 4 small moons. Nix and Hydra were discovered in 2005 by the Hubble Space Telescope. Kerberos and Styx were found subsequently in 2011 and 2012. These small moons have modest sizes. Nix measures about 49 kilometers long. Hydra approximately 43 kilometers. Kerberos and Styx are smaller still, about 12 and 7 kilometers respectively. Their shapes are highly irregular, more resembling misshapen potatoes than regular spheres. These small moons' orbital characteristics are peculiar. They all orbit the Pluto-Charon system's barycenter in nearly circular paths, but their orbital inclinations and eccentricities display puzzling features. Particularly interesting, these moons exhibit chaotic rotation. Nix and Hydra tumble wildly. Their rotational axes and periods constantly change. This chaotic rotation results from irregular gravitational fields created by Pluto and Charon combined. These small moons show significant albedo differences. Nix appears relatively bright. Hydra appears darker. These differences likely reflect variations in surface composition and evolutionary history. Through spectroscopic analysis, scientists detected water ice on Nix's surface, while Hydra's surface shows more organic characteristics. The most widely accepted formation theory for these moons involves a giant impact hypothesis. About 4.5 billion years ago, a large Kuiper belt object collided with proto-Pluto, ejecting material that eventually coalesced into the system. This theory explains why all moons orbit in the same plane and why Charon's composition so closely resembles Pluto's. However, this theory faces challenges. For instance, it struggles to fully explain why small moons have such peculiar orbital parameters and their surface composition differences. New Horizons observations of the moon system brought more surprises. The probe discovered these small moons' surfaces are relatively young, lacking numerous impact craters, suggesting they might have experienced some form of geological activity. Particularly perplexing, the small moons' orbital resonance relationships. They engage in complex gravitational dances. Some moons' orbital periods show simple integer ratios. This orbital resonance helps maintain system stability. Another unique aspect of Pluto's moon system lies in its dynamic environment. Because Pluto and Charon have comparable masses, they collectively create a complex gravitational environment. Within this environment, small moons' orbital evolution experiences multiple influencing factors. Through numerical simulation, scientists found this system might have undergone significant orbital evolution historically. Charon likely formed closer than its current position, then gradually moved outward through tidal interactions. Small moons' orbits might also have changed substantially. Some moons might have been closer to Pluto. Some might even have exchanged orbital positions. This dynamic evolutionary history provides valuable case studies for understanding planetary system formation and evolution. Studying Pluto's moon system also holds importance for understanding other planetary systems. Among exoplanet systems, scientists have discovered several Pluto-Charon-like binary systems. These discoveries suggest such system architectures might not be rare in the universe. Furthermore, small moons' surface materials might provide important clues about early solar system composition. These icy bodies serve as time capsules, preserving primordial material from the solar system's formation. Future exploration missions might specifically study this peculiar moon system. Orbiters could long-term observe system dynamics. Landers could directly analyze moon surface composition. Particularly noteworthy, these moons might host combinations of water, ice, and organics. Under appropriate conditions, such combinations might foster life's precursor substances. Although currently no new missions, specifically targeting Pluto's moons, are planned, scientists are already discussing various possible exploration scenarios, including flyby probes, orbital missions, even surface landers. As observational technology advances, ground-based and space telescopes will continue studying this system. James Webb Space Telescope's infrared capabilities will provide more information about moon surface compositions. Research on Pluto's moon system remains in its early stages. Each new discovery brings more questions. Why are small moons' surfaces so young? What are their internal structures like? Did they ever possess subsurface oceans? These questions require future research. This peculiar moon system continues challenging our understanding. It reminds us, even at the solar system's edge, countless mysteries await exploration. As research deepens, we might discover Pluto and its moons can tell us more stories about solar system formation and evolution. This knowledge matters not just for this distant system itself, but for our broader understanding of the universe. At the edge of our vast solar system lies a mysterious region known as the Kuiper Belt, and Pluto serves as this region's most famous representative. Also, our crucial window into understanding this distant realm. The Kuiper Belt's discovery history traces back to the mid-20th century. In 1951, American astronomer Gerard Kuiper first proposed this theory. He suggested beyond Neptune's orbit should exist a ring of icy bodies. This theory emerged to explain short-period comets' origins. Kuiper speculated this region preserved primordial material from the solar system's formation, serving as a natural laboratory for studying planetary formation processes. However, not until 1992 was this theory confirmed. Astronomers David Jewitt and Jane Liu discovered the first Kuiper Belt object, 1992 QB1. This discovery opened a new chapter in outer solar system exploration. The Kuiper Belt spans considerable space, beginning beyond Neptune's orbit, extending about 55 astronomical units from the Sun. This region's width equals all inner solar system planetary orbits combined. Within this vast space exist tens of thousands of icy bodies, their composition mainly water ice, methane ice, and ammonia ice. These celestial bodies resemble fossils preserved from the solar system's early formation, recording 4.6 billion-year-old history. Pluto, as the Kuiper Belt's largest member, holds special scientific value. Its diameter approximately 2,377 kilometers. Mass about 1/6 the Moon's. These characteristics make it an ideal sample for studying Kuiper Belt objects. Pluto's orbital characteristics are highly typical within the Kuiper Belt. Its orbital eccentricity is large, reaching 0.248. Orbital inclination reaches 17 degrees. Such special orbital parameters are quite common among Kuiper Belt objects. More notably, Pluto and Neptune maintain a 3:2 orbital resonance. This orbital resonance phenomenon forms a special group within the Kuiper Belt, called Plutinos. These objects, like Pluto, all maintain orbital resonance with Neptune. Their orbital periods, approximately 1.5 times Neptune's. This dynamical characteristic provides important clues for studying the solar system's early evolution. Pluto's physical characteristics also reflect Kuiper belt objects' general properties. Its density about 1.86 grams per cubic centimeter. Between ice and rock, this indicates it comprises ice-rock mixtures. By studying Pluto's composition, scientists can infer other Kuiper belt objects' basic makeup. This information holds great significance for understanding the solar system's primordial material distribution. Pluto's surface volatile ices include nitrogen ice, methane ice, and carbon monoxide ice. These substances are widespread in the Kuiper belt, but Pluto enables our first detailed study of their properties and behavior. New Horizons Pluto exploration revealed Kuiper belt objects' geological complexity. In this distant world, we observe active geological processes, young surface features, and complex atmospheric phenomena. These discoveries changed scientists' traditional understanding of Kuiper belt objects. These distant worlds aren't all dead ice balls. They might possess rich geological activity and complex surface evolutionary history. Pluto's atmospheric research also provides references for understanding the Kuiper belt environment. Although most Kuiper belt objects are too small to maintain stable atmospheres, Pluto's example shows some large Kuiper belt objects might possess temporary or seasonal atmospheres. Particularly noteworthy, Pluto's surface color variations, from dark red to bright white. These color differences might reflect space weathering processes experienced by Kuiper belt object surfaces. In Pluto's darker regions, scientists detected tholins' presence. These complex organic molecules might similarly exist on other Kuiper belt object surfaces. Pluto's possible internal structure guides understanding of Kuiper belt objects' thermal evolution. If Pluto indeed possesses a subsurface ocean, then other large Kuiper belt objects might have similar conditions. This possibility greatly expands our understanding of solar system habitable environments. Even in such distant regions, liquid water environments might still exist. This opens new directions for cosmic life research. Pluto's moon system also reflects a Kuiper belt object characteristic. Many large Kuiper belt objects possess their own moon systems. These systems' formation mechanisms likely all relate to impact evolution. By studying the Pluto-Charon system, scientists can better understand binary system prevalence and formation mechanisms in the Kuiper belt. Kuiper belt research extends beyond Pluto itself. This region also contains several other important object groups. Besides previously mentioned Plutinos, there are classical Kuiper belt objects. Their orbits relatively circular, showing no clear orbital resonance with Neptune. Scattered disk objects, their orbits extremely elongated, might have experienced close encounters with Neptune. And detached objects, their orbits highly inclined, might have experienced gravitational perturbations from other planets. Pluto occupies a special position among these object groups. It's the earliest discovered member, also the currently largest known member, and the only closely explored member. After completing Pluto exploration, New Horizons continued flying deeper into the Kuiper belt. Its second target was the small body nicknamed Arrokoth, formally designated 2014 MU-69. This snowman-shaped object showed us more typical Kuiper belt object appearances. Its diameter about 35 kilometers, comprising two lobed sections. Surface displaying particular redness. Compared to Pluto, Arakoth might better preserve the primordial state from the solar system's formation, because it's too small to undergo significant geological evolution. Through comparative study of these two objects, scientists can understand Kuiper belt objects' evolutionary differences at different scales. Kuiper belt research also holds key significance for understanding solar system formation theories. According to standard solar system formation models, Kuiper belt objects should have formed closer to the Sun, later scattered to current orbits during giant planet migration. Pluto and other Kuiper belt objects, orbital characteristics and physical properties, provide important observational evidence for testing this theory. Particularly interesting, Kuiper belt objects' size distribution can help us understand planetesimal accretion processes' specific mechanisms. During early planetary formation, current theories suggest Kuiper belt objects' size distribution should follow certain patterns, but actual observational results show possible anomalies exist. These anomalies might indicate formation processes we don't fully understand yet. Pluto, as the Kuiper belt's representative, also played important roles in planetary definition discussions. Its reclassification prompted astronomers to establish more complete celestial body classification systems. Now, dwarf planets have become an independent celestial body category, including Pluto, and multiple large Kuiper belt objects are classified into this category. This classification holds theoretical significance, also influences future exploration planning. Different celestial body categories might require different exploration strategies and research priorities. As observational technology advances, we're discovering increasingly more Kuiper belt objects. Currently known objects exceed 3,000, but estimates suggest Kuiper belt objects exceeding 100 kilometers diameter might number over 100,000. Deep studies of these objects will help construct more complete pictures of the solar system's edge. While Pluto continues playing a benchmark role, future exploration missions might specifically target other Kuiper belt objects, like Eris, Makemake, etc. These objects' exploration data will form valuable comparisons with Pluto's information. Through such comparative studies, we'll distinguish which features are unique to Pluto, which are common characteristics of Kuiper belt objects. Kuiper belt research also closely relates to other frontier fields, like exoplanet system studies around many other stars. Similar icy body belts have been discovered. By studying the Kuiper belt, we can better understand these exoplanetary belts' properties and evolution, thereby deepening knowledge of planetary systems' universal laws. From broader perspectives, Kuiper belt objects might become important future space exploration targets. Their preserved water ice and other volatiles might provide valuable resources for deep space exploration missions. Although this concept remains distant, some studies already explore possibilities of utilizing Kuiper belt resources to support long-term space missions. Pluto, as the Kuiper belt's representative, will continue playing important roles in astronomical research. Each new discovery enriches our understanding of the outer solar system. As research deepens, we might discover this distant world holds more surprises awaiting us, and each new discovery will help us better understand the solar system our home. On our cosmic exploration journey, Pluto and its Kuiper Belt companions will continue guiding our direction, leading us into deeper cosmic space, solving more mysteries about the solar system's origin and evolution. New Horizons' historic flyby revealed Pluto's astonishing complexity, but also brought more unsolved mysteries. This distant world still guards many unknown secrets, awaiting future missions to uncover. Let's first focus on Pluto's internal structure. Although gravity field measurements suggest it might possess a rocky core, specific composition and structure remain enigmatic. How large exactly is this core? What's its radioactive element content? Does it still retain sufficient heat to drive ongoing geological activity? More profoundly, does Pluto's interior truly host a liquid water ocean? New Horizons data indicate this possibility is quite likely, but requires more evidence for confirmation. If exists, what's this ocean's scale? How about its salinity? Does it contain key ingredients for life? The origin of Pluto's young surface features also represents an important unsolved mystery. What forces continuously reshape this world's surface? Internal heat, or volatile ice seasonal cycles, or both? How do these processes operate continuously in this extremely cold environment? Particularly puzzling, cryovolcanic activity on Pluto. Right, Mons region features indeed resemble cryovolcanoes, but we still need more data for confirmation. If truly cryovolcanoes, what's their eruption composition? What's their eruption frequency? And their heat source's origin? Pluto's atmospheric system equally brims with mysteries. Although we observed complex atmospheric structures, their detailed chemical composition and dynamic processes remain poorly understood. What's the specific atmospheric escape rate? How does this escape affect Pluto's long-term evolution? Regarding the Pluto-Charon system's formation, scientists proposed the giant impact hypothesis, but this theory requires more evidence for refinement. What was the collision's specific process? What were the primordial body's compositions? How did small moons form from post-impact debris? Pluto's seasonal change cycle also brings many unanswered questions. On this world with 248-year orbital period, how do seasonal variations affect atmospheric composition? How do they alter surface features? These questions' answers require long-term observations. New Horizons could only provide a momentary snapshot in Pluto's evolutionary history. We cannot understand its long-term changes from this, like seeing one movie frame, but needing to deduce the entire storyline. Future missions must solve these mysteries. Scientists have proposed various concepts. A Pluto orbiter represents the most anticipated option. Such a probe could orbit Pluto long-term, detailedly studying its surface and atmospheric changes. Designing such an orbiter faces enormous challenges. First, must solve power problems. Due to extreme distance from the Sun, solar panel efficiency is very low. Might require nuclear power systems. Another challenge is orbital insertion. Pluto's gravity is very weak. The probe needs substantial fuel to decelerate into orbit, greatly increasing launch weight and mission costs. More complex are communication issues. Transmitting data from Pluto requires powerful antennas and sophisticated deep space network support. Data transmission rates face strict limitations. Despite these challenges, scientists actively plan next-generation missions. One possible concept involves launching multiple small probes simultaneously, forming an observation network. This could obtain more comprehensive data. Another interesting idea involves deploying balloons or airships in Pluto's system, conducting direct atmospheric detection. Although Pluto's atmosphere is thin, this detection method remains theoretically feasible. Landers also represent important future options. Direct surface sampling and analysis on Pluto could answer many composition questions, especially regarding volatile ices and organics. For Charon and other small moons, we also need specialized exploration. These bodies might preserve crucial information from the solar system's formation. Their geological history equally deserves deep study. International cooperation will be key for future exploration. Due to high mission costs and enormous technical challenges, collaboration between space agencies becomes particularly important. While awaiting new dedicated missions, we can still study Pluto through other methods. James Webb Space Telescope's infrared observations can analyze Pluto's surface chemical composition, monitor its atmospheric changes. New generation ground telescopes, like the 30-meter telescope and extremely large telescope, will also provide clearer observation data. These facilities can continuously monitor the Pluto system, record its long-term changes. Computer simulations also represent important research tools. By establishing precise physical models, scientists can simulate Pluto's internal structure, atmospheric circulation, and geological processes. These simulations, though based on hypotheses, can help us understand observed phenomena and provide theoretical guidance for future missions. Pluto research's significance extends far beyond understanding this single body, can reveal Kuiper Belt objects' universal characteristics. These icy worlds preserve important information from the solar system's formation. By studying Pluto, we can better understand planetary system formation and evolution processes. This knowledge also holds important reference value for studying exoplanet systems. Particularly noteworthy, possible prebiotic chemical processes on Pluto. Although temperatures are extremely low, complex organic molecules indeed exist. How these molecules form in such harsh environments? What are their evolutionary pathways? These represent highly attractive scientific questions. As detection technology advances, we might solve these mysteries. In the near future, new propulsion systems, like ion thrusters and solar sails, could shorten travel time to Pluto. More advanced instruments will provide higher resolution data, more precise analysis results. These technological advances will open new eras in Pluto research. In the foreseeable future, humankind might witness comprehensive exploration of the Pluto system, from orbiters to landers, from atmospheric probes to sample return missions. Each new mission will bring breakthrough discoveries. Pluto's story is far from over, still awaits the next explorer's arrival. This distant world will continue sparking our curiosity, pushing us toward deeper space. Every unknown exploration tests human wisdom, also practices scientific spirit. Pluto's unsolved mysteries await future scientists' solutions. In coming years, we believe this frozen world will bring us more surprises. Each revealed secret will deepen our understanding of the universe. Pluto's exploration journey holds unique and profound significance. In the history of astronomy's development, this distant celestial body not only changed our understanding of solar system structure, but also drove innovation in planetary science theory. Pluto's discovery itself exemplifies the spirit of scientific exploration. Its finding process blended mathematical prediction with observational verification. demonstrating perfect integration of theoretical and experimental science. This history teaches us, even the smallest anomalies may lead us to major discoveries. In planetary science, Pluto prompted us to reconsider the definition of planet as a fundamental concept. The 2006 planetary definition controversy superficially concerned Pluto's status, actually represented planetary science's maturation. This debate promoted establishing more precise and scientific classification systems. Pluto research greatly enriched our understanding of solar system diversity. Before Pluto, scientists believed low-mass bodies should be geologically dead worlds. But New Horizons discoveries completely subverted this notion. Pluto's displayed geological complexity, contrasting sharply with its small size, forced scientists to re-examine driving mechanisms of planetary geological activity. In this distant world, internal heat from radioactive element decay could maintain such active geological processes. This provides important references for understanding other icy bodies' evolution. Pluto's atmospheric research holds special scientific value. In this thin atmosphere, scientists observed complex organics from photochemical reactions. These processes might resemble early Earth's environment, providing unique laboratories for studying life precursor substance formation. Particularly noteworthy, Pluto's atmospheric haze layers, their formation mechanisms and physical properties, show interesting similarities with Titan's. Comparative studies of these haze phenomena in different environments help us understand organic materials' universal behavior in planetary atmospheres. In astrobiology, Pluto's possible subsurface ocean sparks strong scientific interest. This potential water environment, though beneath kilometers-thick ice, might possess basic conditions for sustaining life. If confirmed, would greatly expand habitable zone concepts. Pluto's nitrogen glaciers and volatile ice cycles provide natural laboratories for studying material phase change behavior. At extremely low temperatures, these processes not only occur on Pluto's surface, but might be common on other Kuiper belt objects. Dynamically, the Pluto-Charon binary system offers ideal cases for studying tidal interactions and orbital evolution. This system's unique configuration helps us understand how gravity shapes celestial system long-term evolution. Pluto's orbital characteristics, especially its 3:2 resonance with Neptune, provide important samples for studying planetary system dynamical stability. This orbital resonance mechanism might be common in other planetary systems. In comparative planetology, Pluto became a bridge connecting traditional planets and Kuiper belt objects. Its features differ from both terrestrial planets and ice giants, representing a new planetary body category. Through studying Pluto, scientists established standard models for icy dwarf planets. These models now apply to studying other similar Kuiper belt objects, like Eris, Makemake, etc. Pluto exploration also advanced detection technology. New Horizons mission made important breakthroughs in autonomous control, long-distance communication, and power management. These technological advances will foundation future outer solar system exploration. In scientific methodology, Pluto research demonstrates multidisciplinary integration importance. This field requires combining knowledge from celestial mechanics, geology, atmospheric science, chemistry, and other disciplines. Pluto's geological mapping, surface composition analysis, and internal structure modeling all require close collaboration among different experts. This cooperation model is becoming modern planetary science's exemplar. Historically, Pluto's research journey reflects scientific cognition evolution patterns, from initial vague understanding to subsequent controversy and debate to current deep comprehension. This process embodies science's self-correcting nature. Pluto's case particularly shows how new observational data test and revise existing theories. This evidence-based cognitive updating represents scientific method's essence. In education, Pluto's story became vivid teaching material inspiring scientific interest. Its fate transitions spark widespread public attention to astronomy. This attention conversely promotes science education, popularization, and development. Pluto's visual images, especially that famous heart-shaped feature, play important roles in science communication. These images hold scientific value, also become bridges connecting science and the public. Culturally, Pluto transcends mere scientific object status. It symbolizes human courage exploring unknowns, represents challenging traditional cognition, embodies continuously expanding scientific boundaries. Pluto's international attention also demonstrates scientific research's global nature. From America's Lowell Observatory to Europe's space telescopes to global observation networks, Pluto research always represents international collaboration achievements. Looking forward, Pluto research will continue playing important roles. As more Kuiper Belt objects are discovered, Pluto will serve as reference benchmark, helping us understand these distant worlds' characteristics. Continuous Pluto observations will reveal its long-term change patterns. These data are crucial for establishing icy body evolution models. Theoretically, Pluto challenges existing planet formation theories. Its characteristics and orbital features provide key constraints for studying solar system early evolution. Particularly notable, Pluto might preserve primordial material from solar system formation. These materials' composition and distribution contain important information about planet formation processes. As detection technology advances, we might obtain direct samples from Pluto's interior. These samples might rewrite our understanding of solar system early history. From broader perspectives, Pluto research holds important reference value. For understanding exoplanet system diversity, many exoplanet systems might contain Pluto-like bodies. Through detailed Pluto studies, we can better interpret observation data of these exoplanets, thereby expanding knowledge about planetary system evolution in the universe. Pluto's scientific significance will keep expanding with new discoveries. Solving each mystery might bring new theoretical breakthroughs, pushing entire planetary science field forward. In summary, Pluto is more than a distant celestial body. It symbolizes scientific exploration, witnesses cognitive progress, represents future discovery starting point. Its research value will become more evident over time. In humanity's cosmic exploration journey, Pluto will forever hold special position. It reminds us, scientific development has no end. Cosmic mysteries are limitless, and our exploration will never cease.